Hi, this is Tim Urdan, author of Statistics in Plain English, and in this lesson we are going to learn how the one-way ANOVA works. We're going to look at the formulas that are involved in one-way ANOVA, and then we'll calculate an example and calculate raw scores and turn them into an F value. So let's start with the basics. Let's start with the formulas. And what you're going to end up doing in a one-way ANOVA is you're going to calculate an F value or an F ratio, and you're going to compare that to a critical F value to see if your overall ANOVA is statistically significant. So the F ratio is the ratio of the mean squares or the mean squared deviations between groups, so that's MSB divided by the mean squares error, the MSE. Sometimes the mean squares error is referred to as the mean squares within groups, or the MSW. But in my book, in this example, we'll call it the mean squares error, or the MSE. So how do we get the MSB and the MSE? To find those, that's what these two formulas are for. The mean square between group is the sum of squares, the sum of the square deviations between groups. This is, generally speaking, the difference between a group mean and the overall mean, known as the grand mean or the total mean. So it's the sum of squares between groups divided by k minus 1. And in this, k refers to the number of groups. So say you're comparing the means of 3 different groups. K would be 3, k minus 1 would be 2. So to get the MSB, you take the sum of the squares between groups, divide by the number of groups minus 1. To get the MSE, the mean square error, you get the sum of the square deviations, sum of square deviations error, divided by the total number of cases across all of your groups minus the number of groups that you have. So say we've got 10 cases per group, and we have 3 groups. This capital N would be 30, 10 plus 10 plus 10 being 30, minus 3, because we've got 3 groups, 30 minus 3 would be 27. So that denominator would be 27, and you would divide the sum of the square deviations error by 27. We'll talk about how to calculate the SSE and the SSB now. Let's see. This is the formula for the sum of the square deviations error, the SSE, and here's what it means. Here's how it works. That is a sum sign. That's my drawing of a sum sign, which is not very good. My handwriting's terrible. Sorry about that. But that's the sum of the squared deviations. X means a raw score within a particular group. X bar 1 means the mean for group 1, the average for the first group. So you find the sum of the square deviations within group 1. That means you square the deviations. And then you do the same thing for group 2, sum of the square deviations within group 2. And then that dot, dot, dot means you do that for each group that you have in your analysis. So if you have 3 groups, you'd have the sum of the squared deviations in group 1 plus the sum of the squared deviations in group 2 plus the sum of the squared deviations in group 3. Once you find the squared deviations for each group, within each group, you add all of those together, and that gives you the SSE. So the sum of squares error, or the sum of the squared deviations error, is the sum of the squared deviations within each group all added together. That's what the SSE is. SSB is a little bit different. This means you're finding the sum, and you are finding the sum of the deviations between a group mean and the grand mean, or X bar T for total. And you multiply that deviation, you square that deviation, and you multiply it by the number of cases in the group. So here's how it works. First, to find the X bar T, the grand mean, the total mean, what you do is you add up all of the scores across all of your groups, sum those all together, divide by the total number of scores across all the groups, and you find a mean for the entire population or groups of scores across all of your groups. That's how you find this. If you have the same number of cases in each group, like in my earlier example, I've got 3 groups with 10 kids or 10 cases in each group, then you just have to find, you can find the grand mean by finding each group mean and dividing by the number of groups. So if you've got 3 groups, you find each group mean and you add them together and divide by 3, and that gives you the grand mean. So that's kind of a shortcut, but that only works if you have the same number of cases in each group. Once you have your grand mean, here's how you find your sum of squares between groups. You take one group mean, say this is for group 1, minus the grand mean, square that, multiply that square deviation by the number of cases in group 1. Then you take group 2, take group 2 mean, subtract the grand mean, square that, multiply by the number of cases in group 2. You do that for each group that you have, and then you sum all of those together, and that gives you the sum of squares between groups. That's how you calculate the SSE and the SSB. Once you have the sum of squares, use these 2 formulas. You come over here. Use these 2 formulas to convert the sum of squares into mean squares. Once you have the mean squares, you plug them into this formula to get your F value. And that is all of the formulas. Now, what I'm going to do is I am going to get some raw data and show you how to do all of these calculations, just going through step by step. Okay, so now what I've got is I have a data set, and I have 3 groups of kids. Let's say they're 10-year-olds. I've got 3 kids from Maine, 3 kids from Alabama, and 3 from Arizona. And what we have here is how many hours per day each kid spent looking at a computer screen, be it on a phone, a tablet, or a personal computer. How many hours per day do they spend on a computer screen? First kid in Maine spent 5 hours, second kid spent 3, third kid spent 7, and so on. So we have the raw data from each of these 3 states. I've also calculated the means. So the mean for group 1, which is Maine, 5 hours per day. The mean for Alabama, 5 1/3 hours per day. The mean for the Arizona sample, 2 hours per day. And then I've also calculated the grand mean. And here's how I calculated the grand mean. 5 plus 5.33 plus 2 is 12.33. They all have the same number of cases. Each group has the same number of cases, so I can just add those means up and divide by 3, because there's 3 groups. 12.33 divided by 3 is 4.11, and that's my grand mean. So now this is all of the information that I need to calculate my sum of squares error and my sum of squares between groups. Let's calculate the sum of squares error first. So we subtract the group mean from each individual score within a group, square it, add those all up. So here's how it looks. Individual score minus the group mean squared equals that. 5 minus 5 squared equals 0. 3 minus 5 squared equals 4. 2 squared is 4. 7 minus 5 squared equals 4. Add all those up, and we get 8. So the sum of the square deviations in group 1 is 8. Then we do it for the other 2 groups. And for the Arizona group, we have three minus 2 squared equals 1, 2 minus 2 squared equals 0, 1 minus 2 squared equals 1. The sum of those add all up equals 2. Okay, I had to use my calculator off camera to calculate these squared deviations and add them all up. So now we have our squared deviations for each group. And we have 8 as our squared deviation for group 1, our sum of squared deviations, 18.67, and 2. And then I just have to add those all up. 8 plus 2 is 10. 10 plus 18.67 is 28.67. So that is our SSE, our sum of squared deviations error, is 28.67. Okay, so now that we have our SSE, we can convert that into an MSE, a mean square error, just by dividing this number by the total number of cases, which in this case there's 9 cases, minus the number of groups. There's 3 groups, 9 minus 3 is 6. So and let's do this little calculator. 28.67 divided by 6 equals 4.778, so we're going to round to 4.78. Okay, so that is our mean square error. That's going to be the denominator of our F ratio. And now we're going to go through the whole process of how you calculate a sum of squares between groups and then convert that into an MSB. Okay, so now I've rearranged the board a little bit, took away the raw scores, and we have the average or the mean for group 1, the main group, 5.00, mean for Alabama group, 5.33, mean for the Arizona group, 2.00, and the grand mean over here, 4.11. Now we're going to create a mean square between groups, but first we're going to calculate the sum of squares between groups, and here's how you do it. It is the number of cases in the group. In this case there were 3 times the difference between the group mean and the grand mean squared. So 5 minus 4.11 is 0.89 squared equals 0.7921. Remember, there are 3 cases in the group, so we're going to say 3 times 0.7921 equals 2.376. We're going to round that up to 2.38. That is how we start to calculate the sum of squares between groups. That is for group 1. We're going to repeat that process for groups 2 and group 3. N times 5.33 minus 4.11 gives us 1.22. We got to square that, and we get 1.4884. And that gives us 4.465. We'll round that up to 4.47. And then we'll do the same thing for the Arizona group. Two minus 4.11 is negative 2.11. We're going to square that. And we get 4.4521. We're going to multiply that squared deviation by the number of cases in the group, which is 3. And we get 13.3563. Going to round that up to 13.36. Now remember, now we have to find the sum of all of those to get the sum of squares between groups. So we've got 2.38 plus 4.47 plus 13.36 equals 20.21. So that is our SSB, is 20.21. Now we've got to convert that SSB into an MSB, and to do that we just divide by the number of groups minus 1. There's 3 groups in this analysis. 3 minus 1 is 2. So we're going to take 20.21 divided by 2. It's going to end up being 10.105. We're going to round up to the 100th place, and that gives us 10.11. So our MSB is 10.11. Our MSE is 4.78. Now that we know those two pieces, we can calculate our F value. The F ratio is the MSB divided by the MSE let's see what we get. 10.11 divided by 4.78 equals 2.115. We're going to round 2.12. All right. After all that work, we get an F ratio of 2.12. That's our observed F value. It's observed because it is the one that we calculated. It's not the one that we look up in the table. The one we look up in the table is our critical F value. So here's our observed F value, and now we'll look up the critical F value. All right, so our observed F value is 2.12. Our critical F value we have to look up in Appendix C of the book. And to do this, to use Appendix C, we first have to know the degrees of freedom. The degrees of freedom for a one-way ANOVA for an F ratio is the number of groups minus 1, k minus 1, which in this case was 2, and the number of cases across all of the groups minus the number of groups. There were 9 cases across all of the groups, 3 in each group. There were 3 groups, 9 minus 3 is 6. So our degrees of freedom for this particular problem is 2 and 6. In Appendix C, 2 degrees of freedom between groups, 6 degrees of freedom error, alpha level of 0.05. We find a critical F value of 5.14. Our observed F value is 2.12. Our critical F value is 5.14. Our observed F value does not exceed our critical F value, so our results are not statistically significant. I'm going to draw a graph and show you what this looks like. All right, so we calculated an observed F value of 2.12, and we looked up a critical F value of 5.14. If you look on the graph, this is a F distribution. This would be the critical F value of 5.14. Over here is the region of rejection, which means our observed F value would have to be out here to be considered statistically significant. Our observed F value is 2.12, not in the region of rejection, not statistically significant. And then we just have to say what our results mean. Our F value is not statistically significant, therefore we conclude there is not a difference in the population means of children from Maine, Arizona, and Alabama in the number of hours that they spent on a computer screen. As you know, we have very small sample sizes. Even though we had very big differences between the sample means, a mean of 2 compared to a mean of 5 and 5.33, that's not statistically significant because we had a very small sample size, or very small sample sizes. So we wouldn't want to generalize the results from those samples to the populations that those samples represent, because the results were not statistically significant.